Newton's first law states that an object at rest will remain at rest and an object in motion will remain in motion in a constant state until acted upon by a net external force. This law is also known as the law of inertia. Inertia is the resistance to a change in motion, either speeding up, slowing down, or any change in direction. In this example, a car with a stuffed toy on its hood is driving down the road when it suddenly brakes and the toy falls off. The toy, which was in equilibrium, experienced inertia. It was moving in the same speed and direction as the car until the net force of the car changed. In this demonstration with the nunchucks, it shows circular motion, which could be explained by Newton's second law, but the first law could be applied in the event that one of the nunchucks were to break off. Then it would continue to move tangentially to its path in a straight line at a constant speed. The following example displays uniform motion because the person is able to continue spinning due to inertia. However, he will eventually slow down over time due to the net external forces acting on him, which is Newton's second law. Newton's second law explains objects that are not in equilibrium. It says that the acceleration of an object is directly proportional to the net forces acting on the object and inversely proportional to the object's mass. Mathematically speaking, this is stated as F equals ma. In our example, 3 marbles of different masses are dropped into a container filled with salt. The acceleration of each marble is the same since acceleration is equal to the force of gravity, which is 9.8 meters per second squared. The force of each marble is shown by the depth of the crater it makes when it hits the salt. The first marble has the smallest force to stop the mass, while the third marble has the largest force to stop the heavier mass. Newton's third law is known as the law of action and reaction. This law states simply that for every action there is an equal and opposite reaction. One example involves a balloon that is taped atop a toy car, and as air is being released from the balloon backwards, the car begins to move forward. This evidently shows that the forces acting on 2 objects will be in opposite directions. This is further seen as you see the person on the right kick the other person and both people move, but they move in opposite directions. The person being kicked is pushed backwards while the person kicking also stumbles backwards. They're pushing against each other. Though it may not be as obvious, the forces the two are applying to each other are equal in magnitude. The person kicking is receiving the same magnitude of force as the person being kicked, despite the difference in their masses. We use Newton's cradle to depict all 3 laws of motion. If the balls are viewed as a system, the motion of the system is maintained. The balls continue to move once the ball that was originally pulled back is released and collides with the stationary balls. Once the ball makes contact with the stationary balls, force is applied to make the last ball move, which receives a momentum that is transferred between the balls. The third law is represented since the amount of balls that move is always equal. If 2 balls are pulled back and released, then 2 balls would act similarly on the opposite side once the momentum is transferred to them, showing that every action is equal in magnitude. It's opposite in direction when the 2 balls coming in stop moving after transferring their momentum to the stationary balls, and then the 2 balls go out on the other end. These are the 3 basic ideas that are applied to the physics of motion.